Somewhere in the universe, a star has just died. Not quietly, not peacefully. Its final heartbeat unleashed more energy in just a few seconds than our sun will produce over its entire 10 billion year lifetime. The explosion happened thousands of years ago, and ever since then, its light has been racing through the darkness. It has crossed vast nebulae, past countless stars, and traveled through the empty space between galaxies, never slowing down. Today, that journey comes to an end. Because today, Earth is directly in its path. A beam of radiation is approaching our planet at the speed of light. There is no warning siren, no explosion to watch in the distance, no technology capable of stopping it. By the time humanity realizes what is happening, it will already be too late. This is the story of what would happen if one of the most powerful explosions in the universe found us. It begins with an automated alert. High above Earth, a space telescope built to monitor the most violent events in the universe suddenly detects an extraordinary flash of gamma radiation. Within seconds, NASA's Fermi Gamma Ray Space Telescope confirms the signal. Then the Gehrels Swift Observatory detects it as well. Ground-based observatories across the world begin turning toward the same point in the sky. Astronomers aren't surprised that another gamma ray burst has occurred. These explosions happen somewhere in the observable universe almost every day. What shocks them is where it's pointing. The calculations all agree. Earth lies almost perfectly inside the beam. The radiation is already traveling toward us at the speed of light. No spacecraft can intercept it. No shield can block it. Humanity has no defense. There is only one question left. What exactly is coming? To answer that, we have to travel back to the death of a massive star and witness one of the most violent events nature can produce. What astronomers are looking at isn't just another exploding star. It's one of the most extreme events the universe is capable of producing. To understand why, we have to begin with a star unlike our own. Our sun is an average star. It has enough fuel to shine steadily for about 10 billion years before ending its life quietly as a white dwarf. But some stars are born with more than 20 times the sun's mass. They burn hotter, brighter, and unimaginably faster. Instead of living for billions of years, they exhaust their nuclear fuel in only a few million. For most of their lives, these stars survive through a delicate balance. Gravity constantly tries to crush them inward, while nuclear fusion pushes outward with equal force. As long as fusion continues, the star remains stable. Eventually, that balance breaks. Deep inside the core, the star runs out of fuel capable of producing enough pressure to resist gravity. In less than a second, the core collapses under its own enormous weight. Matter falls inward at nearly a quarter of the speed of light. Temperatures soar into the billions of degrees, and densities become so extreme that atoms themselves can no longer survive. The outcome depends on how massive the star is. Some collapsing cores become neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons on Earth. Others continue collapsing until not even light can escape. A black hole is born. You might imagine that everything simply disappears into it. But the real violence is only beginning. Around the newborn black hole, enormous amounts of gas and stellar debris spiral inward, forming a rapidly rotating disk known as an accretion disk. Friction heats this material to extraordinary temperatures. Magnetic fields, twisted by the star's rapid rotation, become unimaginably powerful. Exactly how these magnetic fields launch enormous jets of matter is still an active area of research. Computer simulations suggest they channel part of the infalling energy into two narrow beams that erupt from the star's poles at speeds incredibly close to the speed of light. These are called relativistic jets. If one of those jets happens to point toward Earth, we observe it as a gamma-ray burst. Ironically, the explosion itself isn't equally bright in every direction. Most of its energy is concentrated into beams only a few degrees wide. That makes gamma-ray bursts something like cosmic searchlights. Stand outside the beam, and the explosion appears far less impressive. Stand inside it, and it becomes one of the brightest events in the observable universe. That simple fact explains one of astronomy's greatest mysteries. Gamma-ray bursts are actually much more common than we observe. We detect only the rare ones whose beams happen to sweep across Earth. But another question remained unanswered for decades. How could astronomers possibly know that these explosions weren't happening somewhere inside our own galaxy? The answer came from an unexpected source, a Cold War mission that was never intended to study the universe at all.